Okay, let's start. Good morning. So this week is going to be all about algebra with matrices. We're really going to sort of officially describe things you can do with matrices. One of them, the most important possibly, of them being matrix multiplication. We're officially going to describe it and start using it. Yeah. But before going into that, we have two concepts that we were supposed to cover last week, but we didn't have time. One-to-oneness and ontoness, and I want to cover those two. And these are related things. These are concepts related to the notion of linear independence and linear span. These are just sort of different ways of looking at the same thing. So again, let me write it here. One-to-oneness is about non-redundancy, as was the case with linear independence. And ontoness is about accessibility, as was the case with linear spans. So this is about accessibility. Okay. Now let's have a look at these definitions. So we call a linear transformation T from Rn to Rm one-to-one. And you can write it like this as well, one-to-one. If you have two vectors, v and w, in your input space, whose images under the transformation T is the same, then really these two vectors have to be the same. In other words, I can say it another way too. I can say that if I put two distinct inputs, I'm going to have two distinct outputs. Okay, aka, so if v is not equal to w, these are both in the input space, then their outputs have to be distinct as well. Okay, perhaps this is somewhat easier to think about. Now, I can move this around a little bit, and I can say the following. If this is the case, then I can send this to the other side, right? So from here, I can move this to the other side. There's a vector in Rm. Send it to the other side. And write it like this. 0 equals this. But then this is going to be even more apparent by the end of this class. But once I have this, because T is a linear transformation, let's do it this way. So T is a linear transformation, which means that I can write it like this. Okay? So here I have the scalar -1, and because T is linear, I can take this -1 inside, and then I can add these two. Okay? Here I just use the axiomatic definition of a linear transformation only. If you want, you can use a matrix, and you're going to realize that if you were to use the matrix, you would again be able to do the same thing. The point is that this is the assumption for ontoness. I'm saying that 0 equals T of this. And I want the conclusion to be v minus w. That is to say, v equals w. That is to say, v minus w, I want to be 0. So here's another way of writing one-to-oneness. I can say here that T is one-to-one if the only solution to the equation T of b equals 0 is, let me say, T of x equals 0 is x equals 0. So the only solution is a trivial solution. This is another way of writing this whole thing. Okay? And indeed, this goes both ways. Let me leave it like this. Okay? And so you see, now we're starting to see why this is related to non-redundancy, because last week, if you remember this summary that I gave for linear independence, it also had something like this, right? It had a condition like this. Then we formulated this using a matrix here, but matrices and linear transformations are the same thing. Okay? So in other words, this one-to-oneness is really about sort of like, so this phrase is there so that we extend our language to talk about transformations. Okay? And similarly, this too we saw last week in the context of accessibility. There we again formulated this using a matrix, but another way of saying this is, let's say for instance, aka any vector in the target, any vector in Rm can be written as a linear combination of columns of T, of columns of T. Again, I'm thinking of T now as a matrix that's columns and rows, and being able to solve this equation, no matter what U is, means that I can always access U in the target using the columns. Okay? Recall that if my transformation is from Rn to Rm, its matrix is m by n. Right? So T is a linear transformation from Rn to Rm, which, according to our conventions, corresponds to an m by n matrix. So so I can think of it like this as well. Which means that the columns of T are going to be m-dimensional vectors, right? So this is the number of rows in T. That means that columns of T are m-dimensional. So R in Rm, so that everything matches. Okay? Oh, let me add one final thing here. We can also, of course, connect this to linear independence of columns. And I can also say that this is also equivalent to saying that the columns of T are linearly independent. Okay, these are all related, and you can sort of use whichever characterization you want to figure it out. Now, these are somewhat abstract. Let's think of some examples. And here's a table. So for instance, this box represents, so I want to put here an example of a linear transformation or a matrix that is both one-to-one and onto. And here I want to put a linear transformation that is one-to-one but not onto. Could any of you give any example to any one of these boxes?
Matrices that is not onto or one-to-one, could it just be just zeros?
Yes. This is a simple example. Let me give another example. This was the one that I had in mind. It is slightly less trivial. So this is one example. Another example is, for instance, 1, 0, 0, 0. This is a matrix that is, or it's a linear transformation that is neither one-to-one nor onto. Okay? So let's figure this out. My transformation is 1, 0, 0, 0. So this is a matrix notation. In transformation notation, I would write it like this. R2 to R2. Now, if I multiply this with xy, I just get x0. That is to say, in transformation notation, I can just write t of x comma y equals x comma 0. Oh, but you see, this is a transformation that nearly erases the second coordinate. This is what is called a projection. You're projecting onto the first axis. And note that this is not one-to-one because, so not one-to-one. Well, t of 1, 0 is the same thing as t of 1, comma 1, right? Both of these are equal to 1, 0. But according to our condition, if t of v equals t of w, it must be the case, in order for a transformation to be one-to-one, that v has to be equal to w. But in this case, this is my v. This is v. This is w. Their images under t is the same, but v is not equal to w. Okay? Does this make sense? Now, how can I think of this geometrically? Geometrically, this transformation does the following. It takes any vector whatsoever, and all it does is zeroing out the second coordinate, which means that you take this and you collapse it here, right? You sort of like project it to the x coordinate. So if this is v, this is going to be t of v, which means that any vertical line under t is going to be collapsed to a point. Okay? This whole line is collapsed to this particular point. So t collapses this whole line to the point, let's say triangle. And here's triangle. So it cannot be one-to-one. Okay? How about ontoness? How can I argue, or how can I verify that this transformation is not one-to-one? Any ideas? All right, I guess I can write it there.
For it to not be onto, and it's a 2 by 2, you say that because it doesn't cover the entire plane.
Exactly.
It's not onto?
Right? Because you're losing information if you apply t. which means that you won't be able to solve for any output value whatsoever. So not onto. For instance, t of x comma y equals, let's say, 0, 1. This equation, or in terms of matrices, axy equals 0, 1, this has no solution. Okay? Because 0, 1 has some height, but t collapses any vector to the x coordinate. Okay? Or in terms of the columns, I can think of it like this too. You see, the columns of A are 1, 0, and 0, 0. I can only move in the x coordinate. So I won't be able to access any point on the plane using the columns unless that point is on the x coordinate, x-axis. Okay? So it's not onto. Okay? Does this make sense? Okay. So this is one example. Let's move on. I have 3 more boxes, which means that I need at least 3 more examples. I want a transformation, for instance, that is both one-to-one and onto. Yeah.
Would like 0 or 1, 0, 0, 1?
Exactly, right? So that's sort of what we called the identity transformation. If the identity transformation doesn't satisfy everything, then we can't do anything, right? So this should be both one-to-one and onto. I'll leave that to you to verify. Let's do a slightly more complicated example. Let's say 0, 1, minus 1, 0. Okay, this is also an example. This is one example, 0, 1, minus 1, 0. Of course, last week we saw this matrix. This is a rotation matrix. Could anyone tell me how I can describe this as a rotation geometrically? So which way do I rotate the plane, or by which angle?
Flip it across the x-axis.
I want a rotation. How do I need an angle. Tell me an angle.
90 degrees counterclockwise.
Okay, so it's 90 degrees, but it's not quite counterclockwise. Clockwise, right? The other way around. Or, 270 degrees in counterclockwise direction, of course. It doesn't matter. But so recall that so this is the way to imagine 2 by 2 matrices. I look at the first column. First column tells me where the 1, 0 vector goes. Okay? Let's try it again, because this is important to be able to do. One 0 goes to 0 minus 1. Okay? So it's rotation this way. And 0, 1 goes to 1, 0. So this is rotation by 90 degrees in clockwise direction, or it's rotation by 270 degrees in the counterclockwise direction. So let's write it like this. So rotation by pi over 2 in clockwise direction. Okay? Now this is both one-to-one and onto, I claim. So one-to-one. Let's, instead of using this, let's just go ahead and try using, where did I write it? That top condition. So I look at a of xy equals 0. Okay? What is this? This is merely y minus x. Y minus x, I want to be equal to 0, 0. Well, if that is the case, then y has to be 0 and x has to be 0. Well, let me write it like this. xy has to be 0, 0. And by that item over there, this means that this transformation is indeed one-to-one. Which does make sense, right? Because you're just rotating. If you're rotating something, you should be able to rotate it back. And it is also onto so if I write it like this, let's say that I have a target output, let's call it UV. Again, writing this out, this just gives me y minus x, which means that if I were to use, so this has a solution. X has to be minus y. Sorry, x has to be minus v, and y has to be u. So given, so fixed u and v target output, my input, which is minus vu, is going to be a solution to this. That is to say, this transformation is onto. Okay? Does this make sense? So you can think of it geometrically, or you can think of it algebraically. They match, as usual. Okay. How about an example for this? I want a transformation that is one-to-one, but not onto. This is slightly harder. Let me just go ahead and say, this is something that we're going to cover, but if you look at either this cell or this cell, you won't be able to have a square matrix. A square matrix is either both or none, okay? Which means that you're going to have to use some other type of a matrix. Here's an example. If I want one-to-one but not onto, I can use this matrix. Sorry. I want this. Yes. Okay, let's think about this. And it might be a good idea to think of echelon forms as well, you see? So how can I imagine, how can I interpret one-to-oneness and ontoness in terms of the staircases and so on? We haven't discussed how to think of this geometrically, but let's try to figure that out. So my matrix is 1, 0, 0, 1, 0, 0. Okay? So this is a matrix that has 3 rows and 2 columns. Right? So this is an element of 3 by 2, comma r. By what we discussed last week, this means that this defines a transformation from R2 to R3. Takes a 2-dimensional vector, gives back a three-dimensional vector. Okay? So t of x comma y goes to where? Well, all I need to do is to multiply. Let's multiply it here. A times xy is the same thing as 1, 0, 0, 1, 0, 0, xy. This is nothing but x, y, 0. So t of xy is nothing but x, y, 0. How can I think of this geometrically? I have a two-dimensional space here, and t is going from here to three-dimensional space. Let's say this is x, y, z. This is, let's say, x, y. Okay. So this particular 2D vector, 1, 0, now is interpreted to be a vector in a three-dimensional space. For this vector, there is no such thing as the z direction. For this one, its image, there is. Okay? And likewise, 0, 1 goes to 0, 1 here. So here's how I can interpret this t. This transformation t really allows me to think of this two-dimensional plane as a specific plane in 3 dimensions. Okay? Now, clearly this is not onto, right? Because if I were to have in my output space a vector whose z coordinate is not 0, I wouldn't be able to solve the equation. I just don't have the data. Not onto, but it is indeed one-to-one. Of course, I'm choosing these matrices so that it's somewhat straightforward to see and verify these properties. But you can imagine how, given a more complicated matrix, it really requires you to solve certain equations, and it really requires you to be able to do row reduction and so on, right? So, not onto. For instance, let's say 0, 0, 1 has no solution. Because no matter what this is, the z coordinate is always going to be 0 here, based on the definition. So this has no solution. Or in terms of accessibility, I can see that using the columns of my transformation, 1, 0, 0, and 0, 1, 0, it is not the case that I can access anywhere in 3 dimensions. I would be stuck in the xy plane. Okay? And it is one-to-one. Because if a of xy equals 0, 0, using that characterization over there, well, sorry, 0, 0, 0. Well, this is just xy 0. I'm saying xy 0 equals 0, 0, 0, which means that x has to be 0 and y has to be 0. Okay? And here's a trick. If you have a matrix that is here, and if you were to so-called take the transpose of it, which means to interchange rows and columns, you get something here. So if I take this, for instance, Now the first column, I want to be the first row. So 1, 0, 0, and then 0, 1, 0. Okay? Now I'm going to leave that to you as an exercise to verify that indeed this is now onto. So now it's going from 3 dimensions to 2 dimensions, but not 1 to 1. Of course, geometrically, all this matrix does is that it takes a 3-dimensional vector and projects it onto the xy coordinate, xy plane. Right? Clearly, it is not going to be 1 to 1, but it will be onto. Precisely, so it's a situation that is very similar to this. It is projecting, in a sense. Okay? Any questions about this? One-to-oneness and ontoness. Okay. This terminology, even though it is useful, is a little bit clunky. Because both the phrase one-to-one and the phrase onto are adjectives. Okay? That's why some mathematicians came up with alternative names for these that have verb forms, noun forms, and adjective forms, which are somewhat more flexible in use. I'm just going to introduce them. Clearly, you don't need to use them, but if you feel the grammatical sort of problem with using the word onto one-to-one and so on, you might as well. So, one-to-one is, another way of saying this is injective. And then you can say, this transformation is an injection. Right? Now it is a noun form. And then you can use it as a verb as well. This transformation injects. Oh. So one-to-oneness, I'm imagining it to be sort of like a syringe, okay? And onto, for onto you use the word surjective. Surjection, surjects. And this, I'm imagining something like a blanket. Sur is sort of like on top, right? It's like surreal. It's like it allows you to sort of throw a blanket and cover everything. Like these are sort of evocative ways of thinking about this. In any event, some alternative terminology. Any questions about this? Okay. So now let's move on to matrix algebra. Now, first of all, I can add matrices entry-wise, and I can scalar multiply matrices entry-wise. That is to say, this set that we introduced last week of the set of m by n matrices, let me be more explicit perhaps, the set M of m by n, comma r of m by n matrices with real entries is a vector space. And here I'm going to use this index notation. If I have two matrices, what is important here is that they have the same dimensions. I want to define this. Well, I want this matrix to be that matrix whose ijth entry is the sum of the ijth entries of the two matrices. Okay? So now you see we're thinking of a matrix as a vector. Last week or so far we were thinking of vectors as matrices. Now we're doing the other way around as well. So this is vector addition. And scalar multiplication, if I have a matrix A, and if I want to scale this matrix by a number C, it's going to be another matrix whose ijth entry is going to be C times ijth entry of the matrix. Okay? C times A ij. Scalar multiplication. This is a little abstract at this point. Let's do a numerical example. Okay, so here's an example. And of course, if something is a vector space, that is to say, if it's a collection of things that I can vector add and scalar multiply, then that means that I can take linear combinations, I can take linear spans, I can think about linear independence, and so on. So here's an example. Let's let A to be this matrix. So it's a 2 by 3 matrix. If I want, I can write it like this. Right? So here we write the number of rows, and here we write the number of columns. And B, I want to be this other matrix, which is 1, 1, 1, 3, 5, 7. Again, this is a 2 by 3 matrix. So what is, for instance, let's compute A minus 2B. Okay, I'm just going to write everything out. So this is 4, 0, 5, minus 1, 3, 2. Okay, minus 2 times this matrix. Now, scalar multiplying this matrix by this number means I'm just taking this number and distributing to all of the entries so that I get this. So minus 2, minus 2, minus 2, then minus 6, minus 10, minus 14. Okay? And then matrix adding, or vector adding, means that I'm just going to have now one unified 2 by 3 matrix whose entries are the sums of the entries, whose entries are the sums of the corresponding entries. That is to say, this sum is now going to be, again, a 2 by 3 matrix. So let's write it like this. 6 numbers. This number has to be this plus this, which is 2. Okay, and then this plus this is minus 2, and then this plus this is 3. This plus this is minus 7. This plus this is minus 7 again, and then this plus this is minus 12. Okay? Any questions about this? So this is the linear structure. Okay. So here's something you can do with matrices, which is perhaps even more natural. Even if you didn't know how to add and scalar multiply or multiply numbers, you could certainly do this, which is taking the transpose. So this is a new thing that we haven't talked about yet. So matrix transpose. If I have a matrix A with m rows and n columns, then I want its transpose, which I'm going to denote by A to the T, okay, to be an n by m matrix. And by definition, it is this. It is that matrix whose ijth entry is the jith entry of A. Okay? Just flipping the indices, which means that, for instance, using, let's say, A over here, (405) minus 132. If I were to take the transpose, I get the new matrix whose now rows are the columns. So minus 1, 4. Oh, sorry, 4 minus 1. 4 minus 1, 0, 3, 5, 2. Okay, maybe I should draw it like this. Rows became columns now. Okay? You know, this seems somewhat silly to even sort of codify in math, but it turns out this is a very important operation. And we're going to keep using this in more and more contexts. Okay? One thing that is important is that vector addition for matrices and scalar multiplication for matrices use the same space, m of m by n. Whereas if you were to take the transpose of a matrix, unless n is equal to m, that is to say, unless you started with a square matrix, you're going to get something, you're going to get a matrix that is in a different vector space. Okay? Now here's an example, or here's an exercise rather, that I'm not going to discuss. But I think to really appreciate this axiomatic definition of a linear transformation, this is a very good exercise. I'm going to use this curly T, okay? It's a linear transformation that goes from the vector space of m by n matrices to the vector space of n by m matrices that takes a matrix A as an input and as an output produces its transpose. This is a linear transformation. So verify this using the axiomatic definition. Verify this. Using the axiomatic definition of a linear transformation. Now you see we're starting to encounter this self-referential structure of linear algebra that I've been mentioning. We have this operation which we're sort of like describing, but it turns out that operation that is operating on matrices themselves is in and of itself a linear transformation, which means that it has its own matrix, but you see it's not that clear how to represent this as a matrix. We're going to learn how to represent this as a matrix later, but for now we have this axiomatic definition that allows you to verify that something is a linear transformation without using matrix representations. Okay, that's one of the benefits and powers of this functional approach. Okay, it's a very, very good exercise. Okay, like 4 minutes. Any questions? Okay. Let's introduce matrix multiplication then, officially. Let's start with multiplying 2 by 2 matrices. Okay. So maybe I should say matrix multiplication. Multiplication. Let's start with 2 by 2 matrices. Let's let A be that matrix whose entries are A, B, C, D. And let's let B to be the matrix with entries alpha, beta, gamma, and delta. These are just the Greek analogs of these letters. Okay? So I can think of both of these as linear transformations of the plane. So first, let's say I apply A to get some other point on the plane, and then I apply B. Okay? Let's say that the coordinates of this plane is x and y, just to be sort of more explicit about what is going on. And let's say that the coordinates of this plane are u and v. Okay, so this is xy, and then this is uv. So horizontal axis is u, vertical axis is v. If I apply A to a typical vector, I get this. uv, maybe I should write it like this. A times xy is ax plus by, cx plus dy. And I want this to be uv. Take an input, gives you back an output. But then I can take this output and feed it to b, right? B of uv turns out to be alpha u plus beta v, gamma u plus delta v. But then u is this expression, and v is this expression. Okay? I'm not going to finish this today because we're running out of time. Tomorrow, the point is that we're going to realize tomorrow we want to do this, okay? We first take a vector, apply A to it, and that outputs another vector, and then to that output we apply B. I want to define B times A such that this happens. I want a multiplication like this so that this happens. Okay. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today we're going to be primarily focusing on matrix multiplication. And we had started doing this yesterday. This is a specific case. It's a special case. We're again looking at 2 by 2 matrices. And the question is, how do I multiply two 2 by 2 matrices? I can think of 2 by 2 matrices, like we discussed last week, as linear transformations of the plane. And that intuition sort of gives me an idea as to how I should be defining this matrix multiplication. So I have an A, a 2 by 2 matrix, and a B, another 2 by 2 matrix. Arbitrary. Entries of A are A, B, C, D, and entries of B are alpha, beta, gamma, and delta. And I would like to make sense of this expression, BA, B times A, so that for any input vector, xy, I have this equation. That is to say, whatever this is, this BA matrix is, it should be equivalent to first applying A to your matrix, to your vector, and then to that output B. Okay? Now, once you have that, you would easily, you could safely get rid of these parentheses, because it doesn't matter how you combine things, right? You can either first combine these two and then apply it to here, or you can first apply A to this and then combine. And graphically, this is what is happening. I want an A, takes xy, sends it to, let's say, uv, and then B takes the output of A and sends it to some other place. I didn't write down the names for the horizontal and vertical axis in this particular plane because that's not necessarily needed. And I want a matrix BA that takes, it's going to be another 2 by 2 matrix, right? Because it's a transformation of the plane to itself. And I want it to be equivalent to applying first A and then B. All I need to do is to write down this expression. Okay, let's write it down. So, let me be even more explicit. So, uv, according to that graph, is the same thing as A xy. A is A, B, C, D. So I can write it like this. And then we know now that this is AX plus BY, and then CX plus DY. And likewise, B of UV, which is the output here, is alpha, beta, gamma, delta times UV, which again, using the same idea, I have this. But then, I can take this expression and substitute it for U. And likewise, I can take this expression over here and substitute it for V. And that's what I'm going to do precisely. Let me continue from here. So, alpha, open paren, AX plus BY, okay, plus beta, open paren, this, CX plus dy. That's the first row. The second row is gamma and delta. Okay? Just substituted things. Now let me expand all this stuff. So let me just draw this bar here to denote that this is a 2 by 1 matrix. It's a vector still. It's just that its entries are sophisticated looking, let's say. Now expanding, I get this. Again, this is going to be a 2 by 2 matrix. So this is alpha AX plus alpha BY plus beta CX plus beta DY is the first row. And then the second row is gamma AX plus gamma BY plus delta CX plus delta dy. Okay? Now, at the end, I want to display this as some matrix applied to xy. This suggests that I should combine the x terms and the y terms. Okay, let me do that. So this is alpha A plus beta C times x plus alpha B plus beta D y is the first row. And then the second row is gamma A plus delta C x plus gamma B plus delta D times y. That is to say, this is equal to this. So if this is to hold, then that means that B times A ought to be defined this way. Okay? And indeed, this is a definition. Writing it out again, so now we have the formula. So I have, let me now use, instead of letters, let me use indices, because that's sort of what you're going to use more often. Let's say that this is B11, B12, B21, B22, multiplied by A11, A12, A21, A22. Now recall, when we're writing indices for matrices, the common convention is to use double indices, and the first index denotes the row, and the second index denotes the column. So that this is, for instance, the entry at the first row and the second column. And likewise here. I'm being consistent here. And I want this multiplication to be equal to this. Sorry. 2, 1. And then B11, A12 plus B12, A22. And then here I have B21, A11 plus B22, A21. Then B21, A12 plus B22, A22. Now, what is the pattern here? The way to think of this, or remember this, is to do the following. Whenever you're trying to multiply two matrices, this is true generally speaking, but specifically for 2 by 2 matrices, think of the left one as a bunch of rows, right? So lump the rows together and lump the columns of the right matrix. Okay? Now, when you take, for instance, the first row against the first column, you get this entry. Okay? So you see this is the first entry of the first row, second entry of the first row. And likewise, this is the first entry of the first column, second entry of the first column. Okay? The way I imagine this is that I take this row, I hit it against this. Okay? I turn it like this, hit it against this, and I get this thing. Okay, so put it here, then put it there, and so on. Okay, this is the idea. Let's do a couple of numerical examples. For instance, let's look at these matrices. Five, 1, 3 minus 2 is the first matrix. The second matrix is 2, 0, 4, 3. And then the third matrix, I'm going to use this special notation, which is I. Okay? I for identity. This we had discussed before already. And I'm just going to use it again. Okay. Now let's do a bunch of calculations, also incorporating this vector space structure of matrices. So not only can I multiply 2 by 2 matrices, matrix multiplication, but I can scalar multiply them and I can add them. Right? I have 3 different operations. So let's start like this. What is A times B? Well, I'm going to write it down. Okay. So I lump the rows of the left one, and I lump the columns of the right one. And I know that the end result is a 2 by 2 matrix. This entry is going to be given by the first row against the first column. So 5 times 2 is 10, plus 1 times 4 is 4, which is 14. Okay? I'm just writing down this, I'm just using this definition. And then 5 times 0 is 0, plus 1 times 3 is 3. 3 times 2 is 6, plus minus 2 times 4 is minus 8, which gives me minus 2. And then again here gives me minus 6. Okay, this is A times B, a new 2 by 2 matrix. Let's look at another one. Let's do B times A. Now if I've changed the order, right? So this now is going to be 2, 0, 4, 3, and then 5, 1, 3, minus 2. The rule is, again, to split the leftmost matrix into rows and split the right matrix into columns. So you see now we're going to get another 2 by 2 matrix, but it's not going to be the same. This by this is giving me 10, plus 0 times 3 is 0. So this entry is 10. Okay? It's not the same matrix already. But let's finish this up. This gives you 2. This gives you 29. And then this gives you minus 2. Okay? Now, what is important is that we have this notion of multiplication for 2 by 2 matrices. And in a second, I'm going to give you the general matrix multiplication definition as well. But it's not quite working the same way as you would multiply regular matrices. Sometimes, we're going to see a lot of examples of this. Sometimes AB is going to be equal to BA for some other matrices. But generally speaking, AB is not going to be equal to BA. And the way people summarize this is often by saying that matrix multiplication is not commutative. So matrix multiplication is not commutative. Okay, this is the term of art. When you can do this switch, you call it like It's a commutation. Okay? Is this making sense? Okay. Let's do more examples. I'm just going to keep using the same matrices, and I'm going to do a couple of calculations. I think I want to continue from there. This is bad form when you're using the board, but you don't want to go back and do things, but continue from above. Okay, what else should we do? For instance, now that I have a matrix multiplication, certainly I can compute a squared. Okay, we can take squares of numbers. Now we can take squares of matrices. Okay, of course I can do a cubed and so on as well, but let's just focus on a squared. Now this is just a times a. Okay, the operations are the same. So 5, 1, 3 minus 2, 5, 1, 3 minus 2. Now let's multiply. Again, it's going to be a 2 by 2 matrix. 25 plus 3 is 28. 5 minus 2 is 3. 15 minus 6 is 9. 3 plus 4 is 7. That's the square root of the matrix A. Okay? So that's square root of the matrix A. Now we can also go backwards and you can ask, given a matrix, does it have a square root? Okay? That's a nice question, but perhaps at this point it is slightly more sophisticated. As usual, taking powers is much easier when the power is an integer, let's say. Okay, let's do another thing. For instance, let me compute a times I. Okay, I'm just going to write it down again. 5, 1, 3 minus 2, 1, 0, 0, 1. Okay, it's going to be a 2 by 2 matrix. 5 times 1 is 5, plus 1 times 0 is 0, so this is 5. And then 5 times this is 0, plus 1 times 1 is 1. And if you keep going, you're going to realize that you get back a. Now, last week we called I the identity transformation, and now we have sort of like an algebraic reason to do that as well. I, this particular square matrix, is also acting as the identity element with respect to matrix multiplication. Okay? And I'm just going to leave it to you. If I were to switch the orders and first take I and then B, first take I and then A, I would get back A. Okay? So I is acting as both the left identity and the right identity for matrix multiplication. Let me write that down. So I, which is 1, 0, 0, 1, is identity with respect to matrix multiplication. Let me also mention that built into this definition is our geometric understanding of first applying A as a linear transformation of the plane, and then B corresponding to this particular matrix. So all of these multiplications, even though they look algebraic, they have a corresponding geometric interpretation, okay? And it's going to be important in this class to be able to switch between the two ways of thinking about the same thing, or 15 ways of thinking about the same thing. Okay? Any questions? Okay. So now let's make things even more complicated. Again, I'm going to keep using the same matrices, but I want to introduce how I want to introduce the other operations we can use. For instance, addition. Okay? Now, I'm not going to go through all the axiomatics of this matrix multiplication and so on, because at this stage, I think what is most important is that you do lots of exercises and sort of discover the rules yourselves. Or, if you need, you can just go to Wikipedia or something. Because, if you just list down all the axioms, they're not quite easy to use. 5. Let's do this, for instance. A times B plus I. Okay? So, based on how this is written, first I need to add these two and then multiply the end result, which is going to be a 2 by 2 matrix, by this 2 by 2 matrix. Okay? So let me keep A compact, and let me open up B and I. B was 2, 0, 4, 3. Actually, let's change this a little bit, and let's say minus. Okay? So 2, 0, 4, 3 minus 1, 0, 0, 1. Now, at this stage, so before we were doing this in 2 steps. First, I took this minus inside and then added the terms. Now, let's start doing this in 1 step and just subtract 1 from here and here to get this calculation, get this matrix. And, OK, let me leave it like that. A times, so now it's going to be 1, 0, 4, 2. And now let's multiply this out. Now, if you look at A, it is 5, 1, 3 minus 2. OK, so now we can multiply things. And this is what I like doing, because, I don't know, in my experience, this is faster. That's my lived experience. If I first put the frame as the what type of a matrix I should get, it becomes much faster. So 5 times 1 is 5, and then 4 gives me 9, and then this gives me 2, and then this gives me minus 5, and then this gives me minus 4. OK? Let's compute this. AB minus A. Well, we have both of these matrices. All I need to do is to write it out. So AB is 14, 3 minus 2 minus 6. And then A is here. So minus 5, 1, 3 minus 2. Okay, so all I need to do is to subtract these entries from these entries. There, I should respect their positions. So this is going to give me 9, 2, minus 5, 4. Huh. There's an issue. Oh, sorry. This is a minus. Because this is a minus 2, this is a minus 4. OK, now it's good. OK, so now notice that these two matrices are the same. That is to say, I can take this, and instead of first subtracting, doing the subtraction and then multiplication, just like numbers, I can distribute A, right? So I can say this is the same thing as this. I just distributed A, but I know that I is, it doesn't do anything, so I can just think of it as not existing, is the same thing as this. Okay? So it's no wonder that this turned out to be the same thing as this. So you see, matrix multiplication shares some of the properties that you're very used to from regular multiplication, number multiplication, like distribution of matrix multiplication or addition and so on. But sometimes, and this is the main complexity, when you, sometimes matrix multiplication operates differently. It is more complicated than number multiplication. And this is the main complexity. Matrix multiplication is not commutative. And it turns out that this is somehow just sufficient enough complexity to allow one to model a lot of physical phenomena. And that's why in physics, these commutation relations are what they're called, is very important. And in probably problem set 3, you're going to see some calculations about this. You're going to have to, I'm going to ask you to calculate AB against BA and so on. And while we're at it, let me introduce one further terminology. Because people expect AB to be not equal to BA, in fact, they have a specific name for their difference. It's called a commutator. Okay? Let me add this definition. So for A and B, 2 by 2 matrices, their commutator is by definition the following 2 by 2 matrix. I'm just going to take AB, subtract from it BA. And the specific notation for this is open bracket, square bracket, A comma B, close bracket. Turns out that in practice, you really want to be able to pretend that these are numbers. You really want this to be equal to this, okay? But alas, it doesn't happen. Generally speaking, it doesn't happen. So what you do is, the extent to which AB is not equal to BA, which literally is this, you call something else, okay? You call the error something else, and now you focus on this, okay? You try to control this. You try to, use it in a sense. That's why this is important. Okay? Any questions about any of this?
What is that supposed to show?
This? Well, I mean, you can think of it like this, right? So, okay. First, you wear your socks, and then on top of that, you wear your shoes. You can do it the other way around too. Okay? The distinction between first wearing your shoes and then your socks on top of your shoes, and first wearing your socks and then your shoes, like a regular person, is the commutator.
So is it like a transformation
It is a transformation in and of itself. That's true. So perhaps I should draw a picture like this. So from here, let's go there. So I have here the plane. First, I apply to it A, and then, sorry. Let me first apply B, and then A. Okay, it's somewhere. So the end result here is AB. You first apply B, which means that B has to be to the right, because we're sort of applying matrices from this side. I can also do this. I can first apply A and then B. Now, if I keep track of a point of an input here, this goes to, let's say, here, and then this goes to here. Okay? Now, typically, applying B to this point is going to bring it to here, but applying A to the same point is going to bring it somewhere else, let's say here. And then next, applying B to this new point is going to bring it here. Okay? Now, you look at the ghost of this point, somewhere here. This distance, or this difference, is a commutator. How much you earned by switching the orders. Okay? There are more sophisticated explanations of this, but I think at this point this is sufficient. Any more questions? This is very important, okay? So on the one hand, this course is going to require you to be able to think of matrices pretty much as numbers when it comes to algebra, or rather arithmetic. But then every once in a while, you're going to have to, or rather quite often, you're going to have to keep in mind that you cannot quite change the orders of things. Okay? Good? Yes?
Is there an easy example of like when you want to be able to change the order but you're unable to?
Here's an example. I started with that.
I mean like in a real setting, like with context.
In the problem set, I think you're going to see some examples. I'm going to give you not just arbitrary matrices, but matrices that are physically relevant. So I think you're going to look at the commutation relations for Pauli matrices and Heisenberg matrices. That's like a very nice exercise that I quite like. Okay. Any other questions? Oh, well, I mean, so here's another way of thinking about this. Here's another, so I can come up with matrices that are rather straightforward to interpret geometrically, and we can sort of like try to understand. Okay. My chalk. Okay, so here's another example. This is an example where we're trying to think of AB and B, or AB against BA geometrically. let me let A to be this, 1, 0, 0, 0. Okay. Now, this is a projection matrix, right? This is a matrix that if you feed xy to it, just produces x0. That is to say, it just collapses the whole plane onto the x-axis. So this is a projection. Onto the x-axis. I'm not necessarily saying that this is an onto transformation. I'm saying it is onto the x-axis. And let's let B okay, I might mess this up, but we're going to see. Let's be this. So this is shear transformation. This shears along the y-axis. Last week we saw shear along the x-axis. It was just 1, 1, 0, 1. Now this is 1, 0, 1, 1. Okay. Let's first do first A, then B. Let's just multiply this first to verify. So B times A is 1, 0, 1, 1, and then 1, 0, 0, 0. This is just 1, 0, 1, 0. And then A times B is the same multiplication, but with the orders reversed. 1, 0. Okay, good. It's a different matrix. So 1, 0, 0, 0. And I can write, for instance, that AB, so the commutator of A against B is AB minus BA, which is 1, 0, 0, 0 minus 1, 0, 1, 0. That is to say, this is just 0, 0, minus 1, 0. So they don't commute, okay? AB is not equal to BA, which is clear from here too. But this sort of represents the same thing geometrically. Okay? So now let's try to see this geometrically. Okay, let's look at first BA. So this is BA. Okay. First applying A means that I'm collapsing everything to the x-axis. Okay. All these lines are collapsed to the points of their intersection with the x-axis. Now when I apply B to any one of these points, let me just do it here. Any such point is going to be of this form, right? Which means that this is going to look like this, x, and then x. So what you're going to do here is, once you have this point, so from here we have this point, and from here you look at y equals x, and B allows you to move this horizontal point to the point on the y equals x axis. Let's do it the other way around. If you first apply B, so So this is A times B. You see, if I feed 0, 1 to this matrix, I'm just picking out the second column, which means that B is doing nothing for the y-axis, but certainly, if I were to look at what it does to 1, 0, it shears, okay? It shears this line to y equals x. Okay? Shears this way. So go up. But then if I apply A, all I'm doing is to project it back, okay? To get back whatever I started with. So A brings everything down. And that's why you don't end up at the same place. Okay? Any other questions? Did this sort of somewhat answer your question? Okay. So now let's generalize this to arbitrary matrices. What is really most important here when it comes to matrix multiplication is to be able to first use one matrix and then the other one, which means that the output of the first matrix has to match with the input of the second matrix. And that's the only restriction you have, really. In the case of 2 by 2 matrices, both inputs and outputs are two-dimensional, so there is not an issue. General matrix multiplication. So if I'm trying to multiply A and B in this way, okay, let me first back down a little bit. All right. So if I have A, an M by N matrix, it's a linear transformation from Rn to Rm, right? So the transformation corresponding to A is a linear transformation from Rn to Rm. So if the number of rows is m and the number of columns is n, that means that the input of A is n-dimensional and the output of A is m-dimensional. So so this number of rows is m, and number of columns is n. This is inputs, and this is outputs. Okay? Now, if I want to first apply A, and indeed, let me just write it here like this as well. So let's say the input is V. So A is M by N And V is n-dimensional. Sorry. Okay, I guess the colors match. And then let's use another color. Let's say orange. N against 1. So when I'm applying this matrix to this vector, I need this to match with this. Okay? And at the end, I'm going to get something, which is A times V, which is going to have dimensions m by 1. So it's going to be m by 1. Okay? Which means that if I want to now apply yet another transformation to this, the input it accepts, which is going to be the number of its columns, has to match with the row number of A. Okay? Because that's the dimension of the output of A. Okay. Say B now is yet another matrix whose input is M and output is, let's say, P, which means that it is a P by M matrix. Then can define B times A. Like this, okay? So this is N. This is M as there. But then the number of columns of B is M. So the input dimension of B matches with the output dimension of A, which means that I can first apply this and then this. And then the output is P dimensional. Once you have this, you get to define this matrix. And again, similar to what happened here, in a sense, this and this are going to cancel out, and you're going to be left with this and this here, which means that I should be seeing P against N. This is P, and this is N. Okay? No, I still haven't told you how exactly do you do this. Let me just write down that formula as well, and then tomorrow we're going to spend a lot of time on it also. And I can just use this index notation. So all I need to do is to tell you what the ijth entry of the product is supposed to be. The ijth entry of B times A has to be this. BI1 A1 J, sorry. BI2 A2 J dot dot BI M A MJ. Okay? So you see, this is just this sort of an expression, let's say, where I'm running over entries of B and entries of A. But when I'm using the entries of B, I'm always focusing on the ith row. And I'm always focusing on the jth column of A, on the other hand. So likewise, so you're using this is the ith row of B, and you're using it against the jth column of A. Okay? Just like we did for 2 by 2 matrices, you take the ith row for the left one, and you take the jth column from the right one, and you bump them together. And that's the end result. And whatever number this is, you put it into the ijth entry of the product. And that does define you matrix multiplication. Okay? This is all I wanted to say for today. We're going to keep working on matrix multiplication tomorrow. Thank you. Okay, let's start. Good morning. Today, we're going to keep working on matrix multiplication. Again, I'm going to go over the formula. We're going to write down this explicitly. And then I want to do some examples where now the matrices have not necessarily the same input and output dimension. And then I'd like to spend some time on, I guess, the next step, which is to look at inverses in terms of, so with respect to matrix multiplication. So let me just remind you, the whole idea is that you have two matrices, A and B. A, let's say, is an M by N matrix, and B is a P by M matrix. I just made these numbers up. The point here is that this is the number of columns for A, and this is the number of rows for A. And the number of columns I can think of as the dimension of the input for A, and the number of rows is going to be the dimension of the output. In order for BA to be defined, it has to be the case that the output dimension of A matches with the input dimension of B. So whatever A outputs, you can feed back into B to keep going. Okay? So whenever this happens, B times A is defined. And the consistent way of defining this turns out to be this. So the ijth entry of BA, the product, is going to be this. So this is, so I'm taking certain entries from B, and I'm taking certain entries from A. I'm multiplying these entries. You see, the indices are important here. And then I'm adding all of them up. More specifically, you see, if I want to figure out what the ijth entry of BA is, I fix the ith row of B and the jth column of A. And and the entries run through the ith row of B and the jth column of A. Since the output and input dimensions match, I can really pair these numbers together and get this sum. And I just wanted to introduce this new notation as well, perhaps for some of you. This is sort of like a for loop in math. This just says that add these type of terms where your terms are indexed by k, where k runs from 1 to m. Okay, so this is just a for loop sum using a for loop. Okay, this is just a faster way of writing things. This is the Greek analog of S, which is sigma. It stands for sum. Okay, so now let me write. Here I wrote down the matrices explicitly. So in this configuration, I have B times A, and here I have B. Instead of uppercase letters, I decided to use lowercase letters, but they are the same thing, of course. And I have here again A. Now, as you see, there are m rows in A and n columns in A. Okay? And so the notation that I introduced all the way in, I think, week 1 is that you put here as a subscript for A, this n, to represent that this is the dimension of columns, the dimension of the input. And for the output, you put it to this side. The point is that in order for BA to be defined, the input dimension, which I would again write here, has to match with the output dimension here. Okay? So you should be able to see one number here. If you can see the same number, this multiplication is defined, and it's going to give you a P times n matrix. Okay? So let's write down this product. So it's going to be a matrix, and the usual idea, the idea that we discussed yesterday holds. That is to say, I'm thinking of the rows of the left one and then the columns of the right one. Okay, let me do some calculations over there. So let's say that I want to figure out the top left entry of B times A. That is to say, I want to compute BA sub 1, 1. Okay? According to this formula, this is nothing but this. M A M1. Okay? Let me do another one. For instance, let's say I want to compute the next entry, the 1, 2 entry. Okay? So now, according to that formula, this is going to be this. So you see, I'm adding all the terms, and I'm taking these two indices, and I'm fixing the leftmost index in this product to be the first index here. Okay. So this, when I try to write this down, I sort of keep in mind that the first index, for 4 of these, so I have 4 numbers here, right? So the first index is going to come from here, and then the second index is going to come from here. And then in the middle, I have to have the same indices. And I'm just going to run until I end up with everything. Okay? And in this for loop notation, I would write it like this. Okay. And so let me just start writing this then. I'm just going to use this for loop notation because otherwise it's going to be a humongous matrix, and I don't think I have the space here. And in fact, what I'm going to do is I'm even going to suppress this where k runs from, so the bounds for k. I'm just going to say I have a loop whose index is k. I'm just suppressing that it starts at 1 and ends at m. Okay, so this is the 1, 1 entry. And then 1, 2. Okay. N. Okay, so this is the first row. Now you have the second row, which means that I should be using B2 something. And AK1 because it's the first column. Okay. Finally, I have here, what should I put here in terms of indices? Exactly. Right. Because it's the pth row and then first column. Okay? So this is how you multiply things. Now, I didn't write this down to make it more illuminating, I think. It doesn't really make it any much easier. All I wanted to do here is to convince you that this really is cumbersome, okay? Just come to terms with this. It's like when you're first learning this type of stuff, there's this voice in the back of your head that says, oh, there's an easier way of doing this. And ultimately, if you're like thinking of things at a high level, then there is an easier way. But if you really want to compute things, say you're a physicist, you really need to write things down, okay? And if you're getting confused at any stage in this class, what I would suggest is to actually sit down and write things down very explicitly, slowly, and then things are going to start making more sense, okay? Okay, so now let's do a couple examples. Yesterday we were focusing on square matrices. Let's look at more general matrices. And I'm going to use the matrices that we used on Monday, I think. So here are the two matrices that I want to use. 4, 0, 5, minus 1, 3, 2. B is 1, 1, 1, 3, 5, 7. And then let's say that C is 2, 0. Now, of course, C is also a vector I can think of, but I can also think of it as a 2 by 1 matrix, and everything's going to work out fine. Okay? So now let's think about this. A times B. You see there's an issue now, because A is a 2 by 3 matrix. B2 is a 2 by 3 matrix. Okay? In order for this to make sense, this number would need to be the same thing as this. So this doesn't make sense within the confines of this class. Let me just say it is not syntactic, okay? It is not grammatically correct. Not syntactic. Okay? So this is something that you need to worry about when the number of rows and columns are different. On the other hand, if I were to look at B times A, well, that too is not syntactic, actually. Same problem, because A produces a 2-dimensional input, but then when I put it here, B requires a 3-dimensional input. I think what I had in mind was this. A times B transpose. Okay? So if B is 2 by 3, recall that the transpose of B is 3 by 2. I'm just flipping. So instead of rows, I have columns and vice versa. Now this does make sense. Let's write it out. So, 4, 0, 5, minus 1, 3, 2. This is A. And then B transpose is 1, 1, 1, 3, 5, 7. Okay. Now let's look at the numbers. 2 rows, 3 columns, 3 rows, 2 columns. Okay. At the end, even without doing any calculation, I know that this is going to be a 2 by 2 matrix. So I need to compute 4 entries. So this goes over here. This goes over there. Now to compute this, I need to take the first row of the left one and the first column of the right one. 4 times 1 is 4, 0 times 1 is 0, 5 times 1 is 5, which means that this number should be 9. 4 times 3 is 12, 0 times 5 is 0, 5 times 7 is 35. 12 plus 35 is 47. And that's the number that I have. Okay? So minus 1 times 1, 3 times 1, 2 times 1. So that's 4. And then here, minus 1 times 3 is minus 3. 3 times 5 is 15. And then 2 times 7 is 14. Okay? So this is 29, which means that the result is 26. Okay? Now, for instance, I could have also computed, let's say, B transpose A. Okay? Again, I can just write down the inputs and outputs. So this is 3, 2. But then B transpose takes a 2-dimensional input, produces a 3-dimensional output. Which means that whatever this is will be a 3 by 3 matrix this time. Okay? I'm not going to do this computation. Let's do one thing. Yeah. Let me take, for instance, let me try to take, rather, AC. Okay? It wouldn't work because A takes 3-dimensional inputs. C gives me only 2 dimensions. ABC, so 1, 2, 3, 4. AC. Not syntactic. But of course, I could calculate A transpose C. Because now I'm changing the inputs and outputs. And I know that A is 2, 3, which means that A transpose is 3, 2. Okay? And C is 2, 1. So this matches, and the end result is going to be a 3 by 1 matrix. Okay, let's write it down. So this is 4, 0, 5 is the first column. And then the second column is minus 1, 3, 2. And C is 2, 0. So you can do this multiplication, of course, but you can also think of it like this. If multiplying a matrix by 1, 0 gives me the first column, surely multiplying it by 2, 0 should give me twice the first column. Okay? Another thing I can do, for instance, I can look at c squared, that is to say, c times c. But clearly this doesn't work because the inputs and outputs don't match. But if I were to use transpose, you see, now I would be able to do something. C transpose is 2, 0, 2, 0. Okay? So this is 1, 2, 2. At the end, I'm going to get a 2 by 2 matrix. So in this case, you see, the columns of the left one, and likewise, sorry, the rows of the left one, and likewise the columns of the right one, they're all one-dimensional, which means that I only have one product for each of the entries. So this is 4, and then 0, and then 0, 0. Okay? If I were to do it the other way around, that is to say, if I were to compute C transpose C, that would also be syntactic, but it would give me something else. Okay, so C transpose is 2, 0, written in a row. This is not a tuple, okay? This is what you might call a row vector. I'm not using a comma here. It's a matrix. Now, this is 2 rows, 1 column, 1 row, 2 columns, which means that at the end, I'm just going to get a number. Right? It's going to be a 1 by 1 matrix. That is to say, it's going to be a number. And let me maybe write it explicitly here. It's 1, 1, which is 4, if you want 1, 1. So 1 by 1 matrix is the same thing as a number, of course. Okay? Any questions about any of this? Now, in problem set 3, you're going to encounter a problem where I'm asking you to compute a bunch of different products. And I'm also asking you, does it make sense and so on. And hopefully by the end of it, this is going to become second nature. Always keep in mind the inputs and outputs, and you'll be fine. Let me introduce some terminology here. It turns out that this is so important. You see, in week 1, we sort of talked about multiplying vectors. This is as close as I think one can get, or we're going to get, let's say, in this class, to multiplying vectors. And this is called dot product, or inner product. These are both the same thing. Let me write it like this. For V and W in Rn, their dot product or inner product is the number That is to say, the 1 by 1 matrix obtained this way. So V transpose W. We do it this way. And so what is this? Using our notation, it is K running from 1 to n, because these are n-dimensional, Vk Wk. Okay? This is the inner product, or dot product. This, if you were to do it this way, this is called the outer product, as opposed to the inner product. Okay? This is not as common, but still it is useful. Perhaps I'm not gonna write it here. It's not important at this stage. Okay? Now, toward the end of the class, we're really going to be focusing on this thing, because it turns out that taking dot products of vectors is very important. In particular, it turns out that it is closely related to a notion of angle between them. Okay, so far we haven't talked about the angles between vectors, but eventually we're going to need to. Another notation for this is this: V, and then you put a dot in between, and then you put W. And of course, note that I can write it like this also. So because it doesn't matter in which order I write these two entries. These are numbers. Okay. If this is not clear, it's a good exercise to verify that this indeed too is the same thing as this. Okay. Any questions about any of this? So this is all there is to matrix multiplication. Now the whole world opens. Essentially, the rest of this class is going to be all about figuring out certain implications of the structure that we've built, or we've discovered, perhaps. Okay. Let me give you one exercise. If you want to get proficient at this index managing stuff, a very nice exercise is this. I doubt that you're going to actually need this. You're going to need to be very proficient at index managing, at least for the purposes of this class. But if you want to really become proficient, this is a good exercise. So verify okay? That is to say, if I have 3 matrices, and let's say that multiplication either way is okay in terms of inputs and outputs. But first, you multiply BA, and then you get the result, and then you multiply that by A. I'm saying that this is the same thing as first lumping together the last 2 operators, or transformations, and then using the first operation before them. So this is something that we're familiar with standard number multiplication. It turns out that for matrices too, even though AB is not necessarily equal to BA, generally speaking, this does hold. Okay? And this is called the associative property. Of course, it is not important what it's called. And it is, I hope, somewhat intuitive that this should be the case indeed. Because in terms of transformations, it shouldn't matter in which order you do these, as long as you're going this way. And because of this, you can safely write, so ABC without using parentheses, because this has an unambiguous meaning. Okay? Any questions? Yes.
I was just curious.
Yes.
When I've seen the dot product before, it doesn't ever explicitly state you need to take the transposition of V.
Uh-huh.
But for our purposes, versus?
Well, so here's the thing. So if you're thinking of matrices, or if you're thinking of vectors as matrices, this doesn't make sense in terms of inputs and outputs. Okay? This has to be there. Yeah.
It's basically just vector notation versus doing vectors as matrices.
Exactly. I'm just switching between the interpretations.
Okay.
Yeah. Yeah. So this dot product, this notation is used in more, let's say, highbrow circles. And this is used in more lowbrow circles. Okay? This is like more computational. From a computational point of view, everything in linear algebra is a matrix. So I'm just going to operate on everything like they are matrices. Otherwise, vectors are not matrices, and they deserve their own like specific notation and stuff. Yeah. Of course, there's this other thing. There's this whole field called geometric algebra that also assigns different meanings to putting matrices next to each other. But we're not going to get to that. Okay? So for instance, cross product is another operation you can do in using matrices, using vectors, but we're not going to, I don't think, use that. Okay? Did this sort of answer your question?
Yeah.
Yeah. Yeah. Don't worry too much about notation. It's all a matter of multiplying matrices. Okay? Any other questions? Okay. Let's return back to 2 by 2 matrices. Because I want to talk about what is called the multiplicative inverse. Let's write multiplicative inverses of square matrices. So this multiplicative inverse is a much more limited concept in that it doesn't quite apply to every single matrix whatsoever. It applies to only those matrices whose inputs and output dimensions are the same. That is to say, it applies only to square matrices. Still, that is very important. And so let's think about it. So we started, for instance, with matrix addition. Okay? And then one can realize that if you were to take a matrix, all of whose entries are 0, then that acts as doing nothing with respect to addition. It produces the same thing. And you can, on top of that, talk about an additive inverse. So let me just give an example. So additive identity, I can just think of this, for instance, and I can just call it 0. 0 the matrix. Okay? So if I have A, B, C, D, and if I add 0 to it, perhaps I should write it like this. Well, this sum is just going to give me back A. That is to say, A plus 0, 0 the matrix, equals A. And likewise, 0 plus A is again A. So just like the number 0 adding the matrix 0 to a matrix gives back the same thing. So that's why I might call this the additive identity. And then I can say, oh, if I have an identity with respect to an operation, then I have also, possibly, an inverse with respect to that operation. And of course, for the purposes of addition, this is just minus a. If I add minus a to a, I'm going to get 0. Additive inverse, well, it's just going to be minus a, right? I just put a minus in front of each and every single entry of a, and if I add it to a, I'm going to get 0, the identity. So this is a, b, c, d plus minus a, minus b, minus c, minus d. And then once I consolidate, I get 0, 0, 0, 0, which is 0. 0 the matrix. Okay? Now the same idea holds for multiplication too. But just like how we cannot quite find the sort of multiplicative inverse of every single number, in particular, you cannot find the inverse of 0. There's no such thing as dividing by 0. In matrix multiplication too, inverting matrices is going to be conditional. Sometimes we'll be able to do it, sometimes we won't, even if the matrices that we're working with are square. Okay? Yesterday we discussed how the identity matrix, the matrix that is diagonal and that has 1s on the diagonal and 0s everywhere else, is the identity matrix with respect to multiplication. I denoted this by I. This is 1, 0, 0, 1. I'm just focusing on 2 by 2 matrices. Similar to addition then, in order for, let's say, B, another matrix, to be the inverse of A, it should be the case that want B, and let me use alpha, beta, gamma, and delta as entries, such that A times B equals I, and vice versa, B times A equals I as well. Okay? Now, let's write this out, and let's just focus on this piece, okay? It turns out that if you can find a B that satisfies this, B also satisfies this. This is something interesting, perhaps, but is true. So let's just focus on this equation. In this equation, A we're thinking of as known, and I is a numerical matrix, of course. It is also known. And we don't know what B is. I want to figure out the entries of B as functions of entries of A. So A, B, C, D, alpha, beta, gamma, delta. I want this product to be equal to 1, 0, 0, 1. Let's multiply this out. A alpha plus B gamma, A beta plus B delta, and then C alpha plus D gamma, and then C beta plus D delta. Okay? So now, in order for this to be equal to this matrix, it has to be the case that the corresponding entries are the same. So in order for b to be, let me just write a to the minus 1. Instead of writing 1 over a like a number, this is the more common notation. It must be the case that one, 0, 0, 1 correspond to these. Here I'm thinking of A, B, C, and D as known as the coefficients of my system, and alpha, beta, gamma, and delta as the unknowns. Okay? Okay? But then this is a system of linear equations. It has 4 equations and 4 unknowns. Okay? Now we can put this in a matrix, use row reduction, and solve for alpha, beta, gamma, and delta. I'm going to leave that to you because there's a slightly better way of doing this. Okay? And this is an essence of linear algebra being self-referential. You see, we came up with a problem about like inverting matrices and stuff, and it turned out that at the end of the day, it's just a matter of solving a linear system. So most often, it is the case that you solve the problems of linear algebra with linear algebra. That is not always true in other fields of math. Okay? So let's think about this a little bit. Let's note this, okay? Here I have the product matrix, A times B. And I note that its first column is A applied to the first column of B. Right? The first column of B is alpha, gamma. And if I were to apply the matrix A, B, C, D to the vector alpha, gamma, I would get this vector. And likewise, the second column of the product is A applied to the second column of B. Right? The second column of B is beta delta. And here I'm just seeing the vector that is A times that vector. Maybe I should record that. Let me just write it like this. A times alpha gamma. And this one is A times beta delta. Now recall, alpha, gamma, beta, and delta are unknown. So if you want, they're x, y, z, t, or x1, x2, x3, x4. And so this equation tells me that A times this unknown vector equals 1, 0, the first column here. And then A times the second unknown vector is 0, 1. Okay? So I'm doing a conceptual trick here. But we learned that another way of interpreting these equations is to say that both the vector 1, 0 and 0, 1 is in the span of the columns of A. Okay? In other words, columns of A span the output space R2. In other words, no matter what output I choose, A times some unknown vector equals that output is consistent. Given Fg in R2, the system, given any Fg in R2, F and G are numbers, the system A times xy equals Fg is consistent. It has a solution. Okay? Writing this out explicitly using linear system notation, of course, this is nothing but ax plus by equals f, and cx plus dy equals g, which is precisely the paradigm that problem 2 and problem set 1 was interested in. Any questions so far? Yes.
So this is only true if A is linearly independent, right?
Say again?
This is only true if A is linearly independent.
The columns of A.
Yeah.
Yes. Hmm? That is true. Here I haven't, so I could have formulated this whole thing in terms of linear independence, and we're going to learn later that somehow for square matrices, linear independence ends up being the same thing as span, but it's not as straightforward why that is the case. Perhaps it is straightforward for you, but that requires some discussion, I think. But any other questions so far? This is a conceptual jump. I'm not using anything that we haven't discussed so far. I'm just putting things in different places, and I'm keeping track of the syntax. Everything I wrote is syntactic, it's grammatical, but somehow I'm switching the interpretations. Okay? Any questions? This is really like something that is weird going on here, especially if you're not used to linear algebra, as I'm expecting you guys aren't. Okay. It's the same equation, same numbers. I'm just changing my lens with which I'm looking at the situation.
Would this make it easier to solve for like all of these variables? Like if you split up into the smaller ones, is it easier that way or not really?
I mean, no. So, of course, the punchline is that indeed, eventually, we're going to solve for alpha, beta, gamma, delta. It's just that I'm trying to relate problem set 1, this specific problem in problem set 1, to this particular problem. Yeah. The punchline is that there's an equation, of course, for all of these. I just didn't want to rush this step from there to here. Because if this is the case, then we have an idea as to how to look at this. But finding the equations for alpha, beta, gamma, and delta is still, it requires one more step. Okay? We're going to continue working on this on Friday. Thank you. Okay, let's start. Good morning. So today, we're going to be focusing on inverting matrix multiplication. That is to say, finding inverses. As you see, I wrote multiplicative over there in parentheses because typically when people talk about inverses of matrices, they really mean with respect to multiplication. And again, I wrote square in parentheses because really you can only talk about, or let's say at first glance, you can only talk about the inverses of square matrices. The dimension of the input and output has to be the same. And that's why people don't really say square matrices. You're supposed to understand that it's a square matrix that you're trying to invert. Now, there are other versions of inverse operations that possibly we're going to discuss to some extent toward the end of the class, but they are somewhat more sophisticated. At this point, we just look at square matrices. And even further, we're really looking at 2 by 2 matrices. As usual, 2 by 2 is the sort of important case, I would say. Once you understand 2 by 2 matrices and once you get used to algebra and arithmetic with 2 by 2 matrices, then the rest somewhat becomes easier to manage. So our task is the following. We're given a matrix A with entries A, B, C, D, and we've discussed how this identity matrix 1, 0, 0, 1 is the identity matrix. It's the identity element, let's say, with respect to multiplication. If you take any matrix and multiply it by I, that means you just get back the original matrix. So with respect to that matrix multiplication and with respect to that identity, I can also talk about matrix inverses. That is to say, I want to find a B whose entries, again, I wrote as alpha, beta, gamma, and delta, such that A times B equals identity. Cancels out. I want a matrix that cancels out whatever A is doing. Okay? Now note that when it comes to standard number multiplication, we can't always find the inverse. That is to say, we can't always write down the reciprocal of a number. 0 times x equals 1, interpreted as, as an equation of numbers, has no solution. X would be 1 over 0, and that doesn't make sense for a variety of reasons. And likewise, when it comes to matrices, even for square matrices, it is not always the case that you can find a solution to 1, 0. So you can always find a solution to this equation. That is to say, not all square matrices have inverses. So we need to figure out when a square matrix has an inverse, and if it does have an inverse, we need to be able to find what that matrix is. Now, for now, we're going to think of these two tasks as coupled to each other, but then after first midterm, when we start talking about something called the determinant, we will be able to decouple these two things. So one task is to be able to figure out is to figure out if a matrix has an inverse, and the other is what that is. Okay, these two are really separate things, and it really becomes useful to be able to decouple these two tasks. For now, they are the same thing. So we're going to try to invert a matrix, and if we get stuck somewhere, that will be it. And we're just going to say that it doesn't have any inverse. So here I wrote down that equation, A times B equals I. A includes all the numbers that are known, A, B, C, D, and B includes all the numbers that are unknown. I want to solve for alpha, beta, gamma, and delta that equation. Now, writing out this multiplication explicitly, it gives me this. And again, if I want this 2 by 2 matrix to be equal to identity, it has to be the case that the corresponding entries are the same. Okay, equal to this and so on. And this gives me really a system of 4 linear equations with 4 unknowns, right? So alpha, beta, gamma, and delta are unknown here, and A, B, C, D are known. I can write it in this form, in matrix form, like this. And then I can turn this further into an augmented matrix. Now, as you see, in this case, we have a bunch of zeros here. And I left it to you as an exercise to really use row reduction here to solve the system. This will work, okay? It's just that we're sort of trying to come up with a slightly more convenient way of doing this. Partially because of the fact that there's a bunch of spots here that we're not using, right? This does work, but a lot of the entries are 0. So even though this is a method that would work, we're sort of trying to come up with something that would work and that will be slightly faster, possibly. Last time we were, so the last thing we said was the following. This first column of the product, AB, is really A applied to the first column of B. And likewise, this is the second column. Sorry, this is A applied to the second column of B. And so splitting these two equations, I can think of it like this. So one equation is 1, 0 equals A applied to the vector alpha gamma, the unknown vector. And the other equation is this. Okay. And from this, we observed, based on this problem 2 and problem set 1, that if this is the case, if we want to be able to have solutions to both of these equations, then it must be the case that A times some unknown vector equals whatever output vector has a solution, no matter what the output vector is. That is to say, in order for these two matrix equations to have solutions, it must be the case that, let's write it like this, A, B, C, D, which are the entries of A, X, Y, equals Fg, is consistent for any F and G. For any vector, for any output Fg. Okay? So now in problem 2 of problem set 1, you looked at this problem, and the end result of that, or what was expected, was for you to find the statement that if this is the case, that is to say, if this system has a solution, no matter what f and g is, for fixed a, b, c, d, then it must be the case that AD minus BC is non-zero. Okay? Now in problem set, so in that problem, you're also given that first number, the top left corner, A, is non-zero. But here we don't have that. Still, even if you didn't know that A is non-zero, you would be able to deduce this. Let's just stipulate that this is indeed the case, and this is an obstruction. If this number, right, these four numbers are coming from the entries of my known matrix, if this expression ends up being 0, then all bets are off. I wouldn't be able to find an inverse matrix because I literally cannot solve this system. Okay? And for instance here, certainly 0 times 0 minus 0 times 0 is 0. And in this case, indeed, we cannot find a solution. So going forward, since we're trying to find this b, we're just going to say that this is indeed the case. Otherwise, we won't be able to continue.
So like this is how you would find the determinant of a 2 by 2 matrix? Is there any correlation here, or is it just how?
No, it is, yes, indeed. This is like foreshadowing. Yeah. This is what is called the determinant. So for 2 by 2 matrices, the determinant of that matrix is this expression. And now that we mentioned this, let's record this. This number is so important, so this expression is so important, it has a specific name. So this expression, AD minus BC, is called the determinant. It determines something, okay? Determinant of ABCD. This has a bunch of different notations. Let me not get into that for now because we're going to spend a whole week on this later after the first midterm. For now, the observation is that you do row reduction and you're trying to solve certain systems, or you're trying to, do certain operations with matrices, and somehow this expression just shows up naturally. Okay, that's the observation that I want you to sort of note. In any event, so this is that. This is an obstruction. So how can we continue? Well, let's think of it like this. Now I'm going to think of this equation in terms of transformations. I have, let's say here, xy plane, and I'm applying a to it, and let's say that the output is uv. Now, this equation, if I interpret it in terms of transformation, tells me the following. If a of xy is equal to uv, then it must be the case that in order for that equation to hold, that if I apply b to uv, maybe I should write it like this, I should get back xy. Okay? So one this here. Now, what's the next step? Oh, here's the next step. Now I go back to these two equations, these two matrix equations. I want B, then, if this is the case, I'm getting confused. Well, I guess I do want to do row reduction. Okay, so let's do row reduction, starting with, let's say, the first equation. My unknowns are alpha and gamma. So A, B, C, D, 1, 0. Okay, this is my augmented matrix. But now note that whatever operations that I'm going to do, the point is to simplify this. Okay, when I'm simplifying this, I'm going to be doing certain operations to this right-hand side. But then I'm going to have to do the same thing for the second equation. but the right-hand side for that second equation is different. So what I can do is I can augment not only one vector to one side, but the other one as well. Because I'm just going to do the same operations here. So this is an augmented matrix that keeps track of two distinct outputs, of two distinct outputs. The idea is that if I were to do row reduction to sort of simplify the situation, whatever I do would be equivalent to solving or simplifying this augmented matrix. It's just that this is just a more compact way of writing the same thing, is what I'm trying to say. There's a bunch of zeros that are redundant, and here it is somewhat more memory efficient, if you want to call it that. So we have this. Let's note that if both A and C were 0, again, this would be violated. Okay? Let me note this. Both then star over there so this then star would be violated. How can I see this? Any ideas? So here what I'm trying to say is that now that I know that this system is consistent no matter what the output is, I don't know if A is 0 or non-zero, or I don't know what if C is 0 or non-zero, but I know that they cannot be both 0 simultaneously. That is to say, at least one of them is non-zero. Because I want to use that non-zero entry to start doing row reduction. If I had both zeros here, I wouldn't be able to simplify this. It would be simple, but we would get into some trouble. Any ideas? Yeah.
Well, I have a question.
Yes.
So I see how like if they're both 0, then like your x just goes away.
Yes.
But if your b is equal to f and your d is equal to g, then how like is it still violated? I don't know.
Right. So here, think of A, B, C, D as fixed and f and g variable. That it is true that if you had flexibility here, you could sort of engineer something here. But think of it like this. This is given to you, and this keeps changing. Okay? So let's think of it this way. If this column were all zeros, I know that this output really is a linear combination of the columns. Right? We discussed this. If one of them is 0, that is not letting me move anywhere. And really, if both A and C are 0, that means that I wouldn't be able to find a solution no matter what f and g are. Let me write this. This is sort of like a practice for this linear independence, or rather, this notion of span. So here's how we can think about this. Indeed, A xy is x times AC plus y times BD. But then if both of these are 0, then that means that this is 0. Which means that this linear combination really is just the span of one vector. So this is the span of one vector, which means that in the output space, you can only go in one specific direction, whatever this second column tells you. But certainly, you have 2 degrees of freedom in the output. Okay? So can't span R2. Okay? Another way of saying this green box is to say that the columns of A spans R2, the output space. Okay? Because of this, I have that at least one of them is non-zero. Thus, you've done the case when A is non-zero and the first problem in the first problem set. So 2 cases. But then in this case, so this is problem set 1, problem 2. So I'm not going to do that. Let's just say that C is non-zero. I don't know in this case if A is 0 or not. But still, if I know that C is non-zero, I can work with that. So let me first take the second row and divide it by C to get a 1 here. Okay? 1 d divided by C, 0, 1 over C. Okay? Then I can take A times the second row and subtract it from the first row to get rid of this entry. So 1 d divided by C, 0, 1 over C, and then 0, right? And then here now I'm seeing B minus AD divided by C. Here this is 1, and then this is minus A over C. Okay? So now note that this entry here I can write like so. Minus AD minus BC divided by C. Right? I just multiplied B by C and divided by C so that I can consolidate this expression. And I pulled out a minus because I really want to see AD minus BC somewhere. As we saw, that is sort of like an important expression over there. Okay? Let's continue. So the final state that we're at is this. 0 minus AD minus BC divided by C, right? And then 1 minus A over C. It's the first row. The second row is 1 D divided by C. And then 0, 1 over C. Okay? Now, what can I do now? What is the next stage in row reduction? So this is all good. I can sort of swap it and so on, but let's leave it to the end. I want to do something with this entry here. Can I do something with it? You can multiply it by c. You can indeed multiply it by minus c divided by ad minus bc to make this, turn this into a 1. Right? Because that is valid. Because first, we realize that unless we have this, ad minus bc equals not equal to 0, then all bets are off anyway. And here, in this case, we're assuming that c is non-zero. So it's perfectly valid to look at the reciprocal of this number. That is to say, I can divide 0. So now this is 1. Now this is going to be minus c divided by ad minus bc. And then this is going to be this. Let me just do it here. Minus a over c times minus c divided by ad minus bc. This is simply a divided by ad minus bc. A divided by ad minus bc. And let me just take this and subtract it from the second row to get rid of this entry. 1, this is 0. So now, what do I need to do? This were d divided by c before. So I need to multiply this by minus d divided by c. But when I multiply this by minus d divided by c, I merely get d divided by ad minus bc. And then finally, I need to do something here. So this is going to be 1 over c, right? And then this oh yes, so minus okay, let's write this down. What do I need to do? I'm taking this, I'm subtracting this, oh sorry, I'm taking this and I'm subtracting it from here. So that means that I need to take this entry divided by ad minus bc, multiply it by minus d divided by c, and this I need to subtract from 1 divided by c. Okay? So let's look at this. This is, so this goes over there, ad minus bc, and then minus ad divided by ad minus bc. Sorry about that. Okay, so it's all good now. You see, this cancels out with this, and I have a factor of c here too. This c cancels out with this, and at the end I get nothing but minus b divided by ad minus bc. I'm simply doing row reduction using letters. And the final thing I need to do probably is, or if I want to get the echelon form here, is to flip the rows. And once I flip the rows, I get this. Let me write it bigger. So this is d divided by ad minus bc, and then minus b divided by ad minus bc, and then minus c divided by ad minus bc, a divided by ad minus bc. Okay? We're done. You see, this, the first column that I augmented here is the solution of the first equation there. That is to say, this is the first column of B, And likewise, this column, the second column that I augmented, it came from this second equation, which means that its solution is the second column of B. So this is equal to alpha gamma, and this is equal to beta delta. Okay. I know that this was rather convoluted, but I think it was good that you've been exposed to this idea. What is the outcome of this? The outcome of this is this. It has two outcomes. One of them is telling you how to invert 2 by 2 matrices. You don't need to go through this whole thing if you know these formulas, and you should learn by heart these formulas. At least for 2 by 2 matrices. Thus, B is this matrix, D divided by AD minus BC, A divided by AD minus BC over here, minus B divided by AD minus BC, and minus C divided by AD minus BC. And of course, a faster way of writing this is to just pull out that 1 over AD minus BC because it's a number, to write it like this. D, A, minus B, minus C. Okay? So I can safely now write this. If I want to invert a 2 by 2 matrix, first I know that AD minus BC has to be non-zero, and further that the inverse has this expression. So that is to say, ABCD to the minus 1, so the multiplicative inverse, is this. And how do I keep this in mind? The way I keep this in mind is to do this, okay? I look at this matrix. I flip the entries here. So AD now becomes DA, and then the off diagonals, you put a minus in front. Okay, that's how I remember. Okay? This is a very practical formula. It's important for you to be able to invert matrices rather fast, at least when it comes to 2 by 2 matrices. Okay? Any questions about this so far? How many of you have I lost? Are we good? Okay, let's do examples. Two, 1, 1, 1. What's the inverse? Okay, I know that the inverse is of that form. So there's going to be a number here. Let's first look at the entries. The entries are, so I need to flip these two. So 1, 2. And then here I need to put minuses in front. So minus 1, minus 1. So I need a number here. And the number is, so this number has to be 2 times 1 minus 1 times 1. And what is this? This is 2 minus 1, which is 1, which is nothing, okay? 1 minus 1 minus 1, 2. That's the inverse of this matrix, okay? Let's verify. Two, 1, 1, 1, 1 minus 1 minus 1, 2. Well, it's going to be a 2 by 2 matrix. This by this is 2, minus 1 is 1. This by this is minus 2. Add 2 to it, it's 0. 1 times 1 is 1, minus 1 times 1 is 0. And the final one is 1 also. So it does work, okay? Another example. Let's look at a rotation matrix, okay? Cosine of theta minus sine of theta, sine of theta, cosine of theta. Its inverse, so from this geometric intuition, if r sub theta, as we discussed, is rotation by theta degrees in the counterclockwise direction, surely its inverse should be rotation by theta degrees in the clockwise direction, right? Well, let me write it over there. It is indeed true to think of it this way, but let's verify that our geometric intuition does match with this formula. R sub theta inverse, right? So I need to have a number here, and then the matrix is going to be cosine, cosine, right? The diagonals are the same entries, so they stay the same. And then the off diagonals, I need to put minuses in front, which means that the top right corner is going to be sine, the bottom left corner is going to be minus sine. Oh, but note that cosine of theta is equal to cosine of minus theta, and sine of minus theta is equal to minus sine of theta. That is to say, this is the same thing as cosine of minus theta, sine of minus theta with a minus, and then sine of minus theta here, and then cosine of minus theta there. And of course, what is this number? This number is cosine times cosine, which is cosine squared, minus minus sine times sine, which is sine squared. Cosine squared plus sine squared is 1. From trig. So I don't need to write this number as well. So this means that this is the number. This is the inverse. And indeed, as you note, this is nothing but r sub minus theta. Okay? Why don't you give me a random matrix? I want 4 numbers. Whatever number you want.
22, 7, 17.
You're mean. Okay. Well, so I know that there's a number here, but apart from the number, I can just safely say this. Oh, this is not equal, of course. This is A inverse equals 1 over some number times a matrix. Okay, flip these 2 entries, and then minus here, minus there. Of course, I'm thinking if I were to take a random matrix, probably this number is going to be non-zero. Okay, that's sort of my intuition, but let's figure that out. What is this number that we need to put here? It is 22 times 5 minus 7 times 17. Okay, so what is this? This is 100 plus 10, 110, and then this is 70 plus 49, 119. This is correct. So this is minus 9. Now you can leave it like this, or if you want, you can distribute this number to get an expression. So this is minus 5 divided by 9, 7 divided by 9, 17 divided by 9, 22 divided by 9 with a minus. Okay? That's how you do it.
See, it wasn't too bad.
Yeah, yeah. I mean, for me. But I'm sure you wouldn't be very happy if I were to give this to you on the exam, right? So. I mean, I don't hold grudges, don't worry. And you know, I think I deserved it, so. Okay. Let me do one more example. 4. Okay. So 1, 1, 0, 1. If I were to invert this, okay, so this number that I should put here is 1 times 1 is 1, minus 1 times 0 is 0, which is just 1. The diagonals stay the same. Off diagonals, put a minus. Okay, that's the inverse. This is like a fast way of doing this. This is a nice matrix, of course. It is what is called triangular, upper triangular. And on the main diagonal, you have ones. That makes it rather straightforward to use. And let's look at this. So 2, 1, 1, 1 times 1, 1, 0, 1. This is a 2 by 2 matrix. It's inverse. Now, I can first multiply, of course. And when I multiply these matrices, I get this. So this is 2, 3, 1, 2. If I invert it, 2, 2, and then minus 3, minus 1. And then here I need to put a number. That's going to be 4 minus 3 is 1, which means the inverse of this product is 2 minus 3 minus 1, 2. If I were to instead take the inverses of these matrices and multiply those inverses, I would get back the same thing, except that I need to change the order. Okay? One, 1, 0, 1, when inverted becomes this. 1 minus 1, 0, 1. 2, 1, 1, 1, when inverted becomes 1 minus 1 minus 1, 2. And when I multiply this, I get minus 2, plus 2. And then minus 1 minus 2 is minus 3. This by this is 0. Minus 1 is minus 1. This by this is 0, and then 2. Okay? So this is the formula. So I've been emphasizing how the order of multiplication matters for matrices. That means that other things that you do with matrices also are affected by this. In particular, the inverse of AB, the product, is not A inverse times B inverse, but it's the other way around. Okay? That's an important thing. Any questions about these? This is the first result of this gruesome calculations that I made earlier in this class. The second result that is perhaps more important is that really this method does scale to higher dimensions. There are also formulas like this for higher dimensions, but they're harder to memorize. So I would suggest not trying to memorize them. Instead, know how I derive this formula. So, for higher dimensional, for higher dimensional matrices, we do the following. So, step 1. Want a B such that A times B equals identity. Okay? So treat of B as the unknown, like I did earlier in the class, but maybe this is 3 by 3. Okay? What is important is that just like you can augment vectors, you can augment matrices to matrices. So, step 2. Augment. Okay, now this is the augmented matrix. Step 3, do row reduction from week 1 until row reduce, let's say. If you can get identity on the left side, then you have an inverse, and the inverse is going to be duplicated on the right side, like we did earlier in the class, in today's class. If you get stuck somewhere, if your echelon form is not so that you have sort of this identity matrix on this side, that means that the matrix doesn't have an inverse. So, if it reduces to I and then something here, then star is the B, which is the inverse. If not, any other reduced echelon form, which means that I don't get to get identity here. I might get something here, but if I'm not getting identity here, that means that this matrix is not invertible. Means is not invertible. That is to say, it doesn't have any inverse. Okay? So this is a standard operating procedure to compute the inverses of matrices. So as you see, at the end of the day, it again reduces the row reduction. Any questions about this?
So for higher dimensions, because for like the two-dimensional ones, the determinant can't be equal to 0, otherwise it like doesn't make sense. For higher dimensional ones, it's the same thing. Like
Yes, but the determinant is more complicated.
yeah.
Instead of 2 terms, you have now 6 terms.
Yeah.
So that's one of the complications in this whole business. This notion of the determinant scales like n factorial, where n is the dimension. So in 2 dimensions, you have 2 terms, okay, 2 factorial. In 3 dimensions, you have 6 terms, and if you have a 4-dimensional, it's a 4 by 4 matrix, it has also a determinant which has 4 factorial terms, 24 terms, and so on. It scales up like this, which makes it computationally heavy to compute. But we're going to learn. We're going to learn how to do it. Okay. This is not the end of the story. On Monday, I want to do a couple of numerical examples where I exhibit this procedure. But I'm running out of time. So I think it's a good place to stop here. And I'll see you on Monday. Thank you.